Welcome to the first lecture of the course Advanced Machine Learning, and today we will talk about regression and classification and the basics you will need for this course. I will specifically focus on examples from remote sensing area, especially satellite remote sensing, and close-range applications from agriculture. So first of all, I want to give you a motivation why we actually need to care about machine learning. And for this, I will show you now two examples where machine learning is used to derive relevant information for us. A very recent application is the quantification of nitrogen dioxide, which is an air pollutant, and the change is a result of the curfews to control the coronavirus. You can see here observations from the Copernicus Sentinel-5 satellite that show that especially in Italy and Spain, the emissions drop, and nitrogen dioxide affects the air we breathe and therefore our health and also the climate in general. And such observations and an automatic analysis of this kind of data is a valuable basis for climate monitoring, and it can help to raise the awareness about air quality and our changing climate in general. Another example is the pivot irrigation in Saudi Arabia. What you can see here is a time series of Landsat images from the last 24 years. And these green circles in the images are agricultural fields which are irrigated with groundwater using a circular sprinkler system. And this is called center pivot irrigation. These agricultural fields have a diameter of up to 1 kilometer, so you can imagine that you need a lot of water to irrigate them. And such observations and analysis of this time series data help us to better understand agricultural trends or influences on the water cycle. Moreover, it can build the basis for better environmental planning. So what I showed you are examples where a monitoring of a specific events or the development and change of the Earth's surface is an important goal and for this we need remote sensing and machine learning. So remote sensing offers an efficient, cheap and continuous observation of the whole Earth and its changes. Machine learning allows fast, comprehensive, automatic and objective monitoring. Of course, you could do this manually on your own, but it would be impossible to analyze such a huge amount of data on a regular basis. There are already satellites which observe the Earth completely on a daily basis, and it would be impossible to do this manually on your own without machine learning. And sometimes machine learning can even help us to reveal patterns in the data that we didn't know about before. In this lecture, we will cover two remote sensing tasks, regression and classification. Remember that regression is an estimation of continuous characteristics such as yield or building energy needs. This is based on some observations, for example, the berry size or the size of buildings. And classification, on the other side, is the estimation of discrete semantic information such as land use and land cover. So given observations or derived features from these observations, discrete classes are estimated. So let's start with the basics for regression. Consider you have given some observations which are collected in a feature vector. And a feature vector is a multidimensional vector which contains the single features. And this could be, for example, the red, green, or blue channel of a pixel if you take a picture with your smartphone camera, or various measurements such as temperature, the position, that means the coordinates, or some plant parameters for each plant or for a sample. And given these feature vectors and assign to them some continuous target outputs, the goal is to predict the output given new inputs. And these inputs need to be of the same nature like as the given feature vectors you used before. So if you use the height of plants as feature vectors and an output value such as yield, and you learn a model based on these inputs and outputs, you can only use this model for the new inputs if you also use the plant height as feature. So let's have a look at how we can learn a linear regression model. You've given your observations phi, collected in feature vectors, and the outputs y. The red points are actually your observations, and in our case they are one-dimensional. What we want is to derive a regression model indicated by f. And f depends on feature vectors and some parameters w. These parameters w contain a bias term and the weights. The bias term is the intercept with the y-axis, and the weights wd indicate the direction of the regression line. And d is the number of dimensions. In our case, it's one-dimensional. Of course, you can also use a more complex model, but in our case, it's a linear regression. So what you want to find is the relationship between the input and the output. And in order to achieve that, your estimation is as close as possible to the reference targets, we need to have a look at the loss function. The loss function L is defined by a function delta. And delta does actually compare your estimation and the reference. And the loss function will parallelize huge gaps between the estimation and reference so that you can find parameters which give you small gaps. And this is done in an optimization process. So the loss function is minimized, and it is an iterative process in which the parameters are getting closer and closer to a good solution. And there are different loss functions, and two commonly used ones are the mean squared error and the mean absolute error. So the mean squared error is also called quadratic loss or the L2 loss. What you do here is you take your estimation and the reference and you square the difference between them. The mean absolute error or the L1 loss does not square the difference. Here just the absolute value is taken. And the second one is preferred when you want to have more robust solutions. And when you have a look at these equations, you will see that for the mean squared error, actually the model will see much larger errors than the L1 norm if you have large difference between your estimation and your reference. So the model is much more sensitive to these outliers, which so outliers are examples which are far away from your model. And so the model, when you use mean squared errors, the model wants to adjust too much to these outliers. So if you want to have a more robust solution, it's a good idea to go for the mean absolute error. So now it's important to know how good your model is. And for this, you can have a look at two different errors, the training error and the test error. And both are important when you determine the model. So the training error, also called in-sample error, is the error computed on the same data samples used to learn your model. So all the pairs of feature vectors and target outputs, which are used to compute the loss function value, are also used to compute the training error. In many cases, the loss function value and the training error are the same. But we will see later this is not always the case. And the test error is also called out-of-sample error or generalization error, and this is the error you get on unseen data samples. And this is an independent set of data samples, and this indicates how good your model will behave on other data than your training data. And this is called generalization. If you can determine a model, let's say for grapevine yield estimation, and this would also work for pear yield estimation, you would have a model with a high generalization power. Unfortunately, this is very hard to achieve, and very often it depends on the quality and the variety of your samples from which you derive the model. But it's always good to go for a model with a high generalization power. So let's have a closer look at both arrows. So you have training data from which your model is derived, which is marked in red here. So now imagine you took some measurements and you learned a regression model, in this case a nonlinear one, and with this you can reach a zero training error. But very likely, if you apply a model to unseen data, it will give a high test error. If you alternatively learn a linear model like this, which is also a quite good fit, you will reach a low training error, not a zero one, but a low one. And if you apply it to unseen test data, here you can see this in blue, it will also be a good fit for this. So when we have a closer look at the test error, also known as generalization error, you can detect two components. Assume you have a set of different models. For example, if you take a subset from your whole data set, and for each of these subsets you learn a model. This will give you a set of models for the whole data set. So one of the components is bias. Bias is the difference between the average model and the true model. So the average model is the average over all the models you learned on the different subsets. And if you have a biased model, you always deviate from the true model due to, for example, some simplifications in the biased model is not able to capture the relevant characteristics of your data. The variance indicates the differences between all these models. So if you measure something, you will not always get the same result. And the more these models differ from each other, the higher is the variance. So let's have a look at some example. What you can see here is, here are NDVI values computed from the near-infrared and red channel of an image. And what you want to estimate is the biomass. So for some NDVI values, you know the biomass values, and from a few of them, you want to derive a regression model. These samples are the training data and marked in red. In order to know how good your model is on unseen data, some samples are used to compute the test error. So the test data set is an independent set of the training data set. And the test data points are marked in blue. In the ideal case, we would know the exact relationship. That means the true mathematical function between NDVI and biomass. But in this case, we just don't know it. So that's why we use machine learning-based regression to estimate this relationship. And if we make simplifications and perform linear regression, you will end up with a large bias. So in this case, the gray line is a linear regression line. In here, this will give you a large bias, and the model is inaccurate and not flexible enough. So you do not capture the relevant characteristics of your data. On the other side, we choose a very complex model. You can see here this this gray function is much more flexible and much more adaptive to the data. And so you have a very complex model with a lot of parameters. But in this case, we will end up with an inaccurate model because it's too adaptive to the training data. If we would choose another subset of the training data, we would end up with a very different model, and therefore we have a large variance. So every time you change the subset and the model changes a lot, you will end up with a large variance. And in connection with bias and variance is underfitting and overfitting. This is a behavior which you do not want to have. On the top, you see underfitting. So your model is too simple and does not fit the data. In this case, you have a high bias and low variance. This is easy to detect because you will get a high training error and a high test error. So already during the model estimation, you will see that your model is too simple. Overfitting is not so easy to detect, and actually this is quite dangerous behavior, because you could think that your model is good, but actually it's not. So in this case of overfitting, you have a low bias and a high variance, and if you only look at the training data, you might think that your model is a good fit. But when you look at the test error, you will see that this is not true. Therefore, it is really, really important that you have a look at both errors. So let's have a look why overfitting is actually happening. So when you look at your loss function, you will see that you want your model to exactly predict the training data. So you want the estimations from F to be as close as possible to your reference data. But this is not what you want to have in practice. What you want to have in practice is a model which generalizes well and fits the test data too. So this is a core problem in machine learning, and you can solve it, for example, by introducing a regularization term. This term is an additional term to the loss function, and it encourages the model to pick simpler parameters W. And this is the whole idea of Occam's razor. So Occam's razor says nothing else than it is a good idea to encourage the model to be simple. And if you have multiple hypotheses, the simpler one is usually the correct one. Okay, let's have a look at the regularization term. The term denoted with R is added to the loss function and weighted accordingly. So typical regularizations are the L2 regularization, where you square the values of the parameters, and this prevents the parameters from getting too large. And here you can also see another regularization term, which is the L1 regularization, which contains the absolute values of the parameters. In this case, the parameters are also forced to be sparse. That means that some of the parameters get 0. And in case you use an L2 regularization term, you speak of rich regression, and if you have an L1 regularization term, you speak of lasso regression. So let's have a look at an example. Let's assume you want to determine the parameters of a regression function, where the number of parameters in this case is given by 2. That means you have W1 and you have W2. Now let's say you have observations phi1 and phi2 and an output value of y of 20. You can think of possible solutions, for example, with W1 is 10 and W2 is 5. Another possibility would be to have W1 as minus 1980 and W2 of 1000. But if you now change the observations a bit, for example, because you repeat your measurements, you will see that small changes in the features cause large changes in the outcome of the second solution. That means the solution is too sensitive, too adaptive to your training data. So imagine you change a bit phi1 and phi2, and if you have an output, if you compute the output value, you will see that for the first solution with W1 10 and W2 5, you still will be close to 20. But this is not the case for the second solution. Therefore, it's a good idea to introduce a regularization term. There are also other possibilities for regularization, for example, in neural networks, but in general, it's a good idea to prefer a simpler model if possible. So in the next part of the lecture, we will talk about classification, and you will see that there are a lot of parallels between regression and classification. And again, we start that we consider some feature vectors phi 1 till phi n, and as before, we have some observation, and these observations are collected in these feature vectors. This can be, for example, red, green, blue when you take an image with a camera, or for example, temperature or coordinates or some plant parameters, whatever you can think of and whatever you think will be important for your task. For a classification task, you learn now a function f that assigns a class given an observation phi. So this class is discrete, and you have a set of classes, and this set needs to be predefined. And this classifier f depends on the observations. That means your observations which are collected in the feature vector and your parameters w. So the question is now how to obtain the classifier, and there's a nice text by Mitchell which explains how you can obtain a classifier, and it contains the essential elements you need to learn a classifier. And this text says a computer program is set to learn from experience E with respect to some class of task T and performance measures P if its performance at tasks in T as measured by P improves with experience E. The important part here is to learn from experience E. And this experience is for classification given by input-output pairs. For regression, we had input-output pairs that you have given you feature vectors and the target value you want to estimate, for example, the NDVI, and you want to have the biomass. And now these input-output pairs for classification are given by the feature vectors and class labels. And as I said before, these class labels need to be predefined by you. These input-output pairs are also called training data or labeled data, reference data, or ground truth. It's all the same. Be careful when you talk about ground truth, because this is not really a true view. This is which is existent. It's more like that someone defined a reference and you can refer to this. So let's have a look at linear classification. Linear classification means nothing else than you find a linear decision boundary between the classes you want to separate. And in this example here, you have given input features phi 1 and phi 2. So you have a two-dimensional classification task, and you have given output labels. In this case, you have the class labels urban and forest. And now what you want to have is such a decision boundary. This decision boundary is defined by W, and this W contains the bias term, which is the intercept with the y-axis, and the weights, which indicates the direction of this decision boundary. And the decision boundary is, in this case, exactly the separation between these two classes. In order to determine the parameters, we define a loss function. And this loss function contains a function delta, and delta compares the estimated labels and the reference labels. The goal is that the difference between the estimated labels and the reference label is as small as possible. And this is done via an optimization process by minimizing the loss function. So the question is now how to compare the estimated labels and the reference labels. And for this, it will be very useful to make a transformation from labels to targets. Targets are unit vectors where one is at the position of the class label. So for example, if you have three classes and the sample is assigned to class 2, you will have a target vector of 0, 1, 0. And targets can be easily compared, for example, by multiplying them and sum them up. However, What mostly happens is that your estimation is not only a unique label, but more a score vector which contains the scores or the confidence of the classifier. A commonly used loss function is the cross-entropy loss. It contains the targets and the probabilities p. And the probabilities have the characteristic that they are always between 0 and 1 and that they sum up to 1. And these are exactly the same characteristics as for the targets. In the ideal case, the probabilities equal the targets. And the probabilities are computed with a softmax function. And in the softmax function, you have given y, and y is the output from the classifier. So there are different types of learning. They all have in common that in the beginning you have given some observations, and then based on further information and also depending on the application you want to solve, different paradigms of learning can be used. So the paradigms we are focusing on are supervised learning, semi-supervised learning, unsupervised learning, and self-taught learning. So in the following, I will use images with a red image border indicating labeled data and images with a blue border indicating unlabeled data. So for supervised learning, you only have given labeled data. And the overall goal is to find a decision boundary between these two classes, in our case urban and forest. And as soon as you have learned a decision boundary and you have a test sample, you can assign a class to the test sample depending on which side of the decision boundary it is. And in this case, we can assign the image to the class urban. So for semi-supervised learning, besides the labeled data, you also have given unlabeled data samples. You do not know to which class these unlabeled data samples belong, but they need to belong to one of these two given classes. So for semi-supervised learning, it is exploited the similarity between the labeled and the unlabeled samples. So if you have unlabeled samples of forest, they will be very similar to the labeled samples of forest. And using this, you can learn a better decision boundary between these two classes. And when you have a test sample, you can assign a class to the test sample. In this case, it is urban. So for unsupervised learning, only unlabeled data is given. So you have no idea to which class these unlabeled data samples belong, but what you normally do is you search for groups. And generally, you also need to tell how many groups you want to find. And these groups are so-called clusters, and all samples in one cluster are very similar to each other. In this case, if you integrate further domain knowledge afterwards, you can assign this cluster a class afterwards, but this domain knowledge is not used beforehand. Again, if you have given a test sample, you can assign the test sample to one cluster. And if you have the integrated domain knowledge, you also know that this test sample will belong to the class urban. So another classification paradigm, not so well known but powerful, is self-taught learning. Here, in contrast to semi-supervised learning, also unlabeled data samples are used, but these unlabeled data samples can belong to arbitrary classes. The only restriction is that these unlabeled data samples need to be of the same type as the labeled samples. So if you have RGB images, these unlabeled data samples also need to be RGB images. And what you do here is you exploit the similarity of these labeled samples to all the other unlabeled samples. And instead of using some features you derived from your observations, now the relationships to the unlabeled samples are used as new features. And this is already pointing in the direction of neural networks, because neural networks will work in a similar way. So why is it now so difficult to do a classification? You have different challenges you need to deal with, and one type of challenges arise from the application. So you have a high intra-class variability, and you have a low interclass variability. So you have a lot of variation within one class, but also it happens very often that that classes are similar to each other. So it's very hard to distinguish between them. In remote sensing and also in agriculture application, it's a very common problem that you have only a limited amount of training data. So if you want to learn complex models with a lot of parameters, it's a problem that you do not have enough training data to learn a model in a stable and robust way. Another challenge which arises is based on the method. So it can happen that the model is hard to optimize, so it can be very hard to find optimal parameters, and it might happen that you find a model, but this is not the best model you could determine. Especially when you want to learn a lot of parameters, you can run into computational issues that it takes very long to learn your model. And it's also difficult to tune hyperparameters. So hyperparameters are parameters which change the results and influence the model, but they do not directly describe, for example, the decision boundary. A hyperparameter, for example, is the weight between the data loss and regularization. And sometimes you can have a lot of hyperparameters, and it can be hard to optimize them. So an important thing is that you should choose the method based on the application. So it's not that there's an overall best method for all application, it always depends. And it also is important to know that neural networks might also fail in several applications. So it's not a magic box which works for everything. You need to know which neural network you know, and sometimes it's even better not to use a neural network. I want to talk a bit more about supervised image classification. There are several machine learning tasks related to image interpretation, and depending on what you want to have in the end, you either focus on semantic segmentation or instance segmentation, object detection, or categorization. And let me show you the difference between all these approaches. So for semantic segmentation, each pixel is assigned to one predefined class, and pixels of the same class are grouped together to one semantic segment. So here, for example, you can see one image from the Zurich summer dataset, and so the yellow area indicates that this area is a rail track, and all the pixels which belong to the same class and neighbored are grouped in one semantic segment. In this case, this segment is assigned to the class rail. So for object detection, you detect single objects, for example, cars or trees or whatever you want to find in your images. And generally, you estimate a bounding box. And this bounding box is mostly parallel to the image borders. These bounding boxes can vary in size, and also they can overlap. The problem with this approach is, for example, if you have objects which are very long, and if they have a specific orientation in the image, you will get a very large bounding box where most of the bounding box is not filled with the object. So instance segmentation is another task. It popped up a few years ago, and now a lot of researchers focus on this task. And instance segmentation is a combination of semantic segmentation and object detection. So it's not only that you detect an object with a bounding box, but also you get tight object boundaries. Here you can see an example where single grapevine berries are detected, and you can distinguish between neighbored grapevine berries because they have a border around them. So you can exactly see that one instance is one grapevine berry, and neighbored grapevine berries can be exactly separated from each other. So image categorization focus on whole images or image patches and assign one or multiple labels to this image or image patch. You don't know afterwards where, for example, objects are in the image. You only know that these objects exist in the image or the image patch. So here you can see a data set called Use Immersed Land Use dataset, and it contains classes such as tennis court or tanks or river and so on. So the classical supervised classification procedure can be summarized in the following mind map. So you start with processed satellite images. In these images, you have pixels with class information. These are the labeled pixels, and then all the other pixels are unlabeled data samples because you don't know to which class they belong. But what you want to do is you want to assign them a class. The first step is feature extraction. So you think about your application and you extract features which might be important to distinguish between different classes. These can be, for example, intensities or texture or any other features you can think of. In the classification step, you first learn a classification model, and then you take the learned decision boundary and apply them to the test data. And in the test step, the testing data is based on this learned decision boundary assigned to classes which you defined before. And in the end, you end up with such, for example, land use and land cover map, where each pixel is assigned to one class. In order to evaluate how good your model is, you also do an evaluation step with some performance measures, and you can do some post-processing too. So the classical supervised classification pipeline contains the following steps. First of all, you collect labeled data for training and testing. The training data is used to learn a model, and the test data is used for evaluation, or it's just the data you want to know to which class all the data samples belong to. In the next step, you extract relevant features, and then you have the training step. So you learn a classifier using training data, and in an optional step, you can split away a small subset for an independent optimization of hyperparameters. This is called validation. Optional because it's not always the case that you have hyperparameters for optimization, but if this independent validation set can be used to test different values of hyperparameters and see how your learned model will perform on this validation dataset. In the next step, you classify the testing data. So each data sample is assigned to one of the predefined classes. And last step, you evaluate the learned classification models using the test data or an independent labeled dataset. And this is called evaluation. So the training, test, and evaluation steps are the general steps you perform, and the validation step can also be used to tune your model and find good hyperparameters. Some practical advices for you. First of all, be careful with the training and test splits. There are some rules which need to be kept to ensure that you have a good evaluation afterwards and that you can reliably tell that your model is good or not. You should start with a small subset to get an impression about the behavior of the data. Generally, you have a large data set, and it can be really tedious to use the whole data set when you just want to figure out first how your model will behave. And so just sample a small subset, and then based on the small subset, you get an impression about the behavior of your data set, and then you can use these insights and this knowledge and apply it to the whole set. If you can, try to visualize the data. There are some good visualization techniques like parallel coordinates or TSNE, which helps you to get an impression about your data. It's always good to start with a simple classifier and then increase the complexity. Also, because simple classifiers are generally faster to learn, so you can play around a little bit and get an impression how complex your model needs to be in order to get a result which you are satisfied with. And very important, choose appropriate evaluation measures. There are different ones in different communities, and the evaluation measures should be should fit to what you want to show. For example, it's not a good idea to use an overall accuracy measure when you have classes of different sizes. Here it's necessary to also use the average accuracy. We will talk about this in more detail during the next lectures. And with this, thank you very much.